Hello, can you hear me? Hello there. Hello. Up.
Hello.
Hi. You know what? I think it might have worked now. Maybe the thing didn't load, or I loaded it into the wrong version or something stupid like that. No. Oh, I know what I did wrong. I know what I did wrong. Silly me. I didn't distribute this to the parallel nodes. I'm about to start doing a big crunchy run, I hope.
Okay.
I'm damn. Why is this so? Damn it! I don't want this to. This is super annoying. Oh, there it is. It's finished. Okay, let's try it again. That was dumb on my part. And now I want to try running this in Amazon because interesting.
The thing is, quite a few of them actually do have large vertex degrees.
Well, yeah, I think these ones they do. All right, let's try going up a smidgen here. Okay. Now I have a new tool here, which I think must have failed in this case, but let's try it. Yep, no linear occurrence. Well, I consider those two mildly interesting. Those rules look very long. That's an interesting and non-trivial linear occurrence. So hard to tell what's going on in any of these.
I think the third one is pretty interesting. Because it doesn't have large vertex degrees apparently, but
How can you tell?
well, because we set a limit on them.
Yeah. I think I need I need to change the make pictures function. So here what I'm going to do is I'm just going to multiply each of these things by n. You didn't just modify this file, did you?
Which file? I don't know. Is it SW init?
Yeah, did you just put that back in?
No.
Shoot.
I actually do have it open, but the version I have doesn't have that section.
Okay, let me just look here. Well, that's really weird. I have 2 copies of it open. Oh, that already has a max vertex degree. All right, I'm going to kill this version. Is that going to work correctly? So that's applying Did I get this wrong?
Well, what does specific Wolfram rule test return?
An association.
Wait, actually, I'm not sure this ampersand is in the right place. The one after specific Wolfram rule test, because it's inside of the argument.
I think it might be this.
Your steps became reals instead of integers. Yeah, you should put around them.
That will work, won't it?
I think so.
What the hell do you make of that thing? It's interesting. Whatever it is, it's interesting. It's growing slowly.
Okay, can we run it longer?
Sure. Any other one you want to run longer?
Well, I'm not sure. I mean,
let's run the hedgehog longer.
as soon as the manifolds we really want are not two-dimensional, which means they might be hard to see.
Yeah, I know, but I'd be happy to just see a two-dimensional one coming out here.
Yeah, sure, but if this thing turns out to be manifold, it's not obvious yet.
Right. You know what? Why don't I just do... Yeah, what I really want to do is just say make pictures. Oh, yuck, oh, yuck. All right, what is that puppy? What's that puppy? Well, that just disconnected something. Look at that. All right, let's run that one for a long way. Problem is I want to leave those limiters. Well, I don't think we actually need the limiters that much in this case.
Well, I mean, I assume you can always abort it.
Yeah, but look, wait a minute. This here, yeah, okay. Well, who knows what that does? What's that?
Doesn't look particularly complicated.
Yeah, well, okay. Okay, let's do, one day I'm going to get this the right way around. Do you think that's right? Yes, I think that's right.
I don't think so. No, I think it should be C2.
I'm just going to use generic graph plot visualization here.
Well, yes, that will be faster.
What the hell is that? Well, actually, we'd have to say graph plot 3D to that. Let's try running it a bit longer.
Can you also check what the vertex degrees are?
Yes. Hold on, let's just run it that number of steps. Okay. How do I do the vertex degrees? I had a neat way to do it. How do I do it? Vertex degree.
Just vertex degree of this graph, and then you can do it histogram, right?
Let's just, well, there's nothing too dramatic there, but let's just say max
Can you do
of vertex.
plot range just to all? Because I think it's truncated something.
That's a bit large. How do you get a
Yeah.
log histogram?
Well, there are
So there's at least one very high degree vertex in there. Although I reckon 357. Come on. That's officially known as a splodge. My God. Actually, let's do this. Let's look at the causal net of that thing.
Can we get dimensionalities?
Yes, hold on. It's kind of sad that that's the best way to pick up the dimensionality code, but anyway. Let's just go to 25. Oh, I didn't want them to say final state. That doesn't look flat. That's a log-log plot. That looks...
What is it?
What's that?
Can I understand what this?
It's the mean hypergraph neighborhood volume going out to
As
the
a
diameter.
function of radius.
Yes.
So it's 3-dimensional then.
No, it's a log plot. This is a log-log plot.
Right. So for radius 10, the volume is 1,000.
Oh, great. Well, actually, that's not completely stupid. Look at that. That's a cubic.
Yeah, that's what I'm saying.
Okay. Well, let's try growing it a bit further. That's the causal graph. Well, it's the Big Bang. You know, what can I tell you? If it's three-dimensional, we should see something reasonable in a 3D. Oh my gosh, it's the big splodge.
Well, I mean, it's not necessarily embeddable into Euclidean 3D space.
No, I understand. Well, let's look at the following. Let's do this. Let's look at in here.
I mean, why don't we just do graph 3D?
We will. Just 1 second. Let me just store the thing. I think 30 is about as far as we're going to. Well, I don't know. We might get a bit further. Let's
We can do volumes for more than that, I think.
All right. Let's live dangerously. Let's go to 35. Your code is cranking. Actually, I want to move this to a different file. Once it finally comes back. Okay, I'm not really deleting this. I'm going to say, oops, I'm going to go here. Otherwise, we're not going to be able to keep track of what's going on. Okay. All right. EO35 there. All right. So let's take a look. Let me do one very simple thing here. Let me just do length /@ percent states list. EO35 states list. Ooh, this is slow. Wow.
Well, extracting states list takes some time, and it's symbolic code.
Wow.
Well, how large is it?
Well, its events count is
Can you do
29.
expressions count total in it?
Yes, but oh, there we go. 58,000 things. No linear recurrence. Let's do that's pretty seriously lame. How can that thing be linear? It just looks like nonsense, don't you think? Oh, look at that. It's an exponential. Well, this is an exponential. So if I do ratios, okay.
Huh.
What?
It stabilizes.
Yep, 1.3 times. Not the fine structure constant. Even though Eddington might have tried to make it so, but okay, all right, hold on one second. Let's look back here at. I want to do some other things here. I want to get the final state of this thing, which is pretty big. 35. Let's see, how do I get the adjacency matrix? Okay, that's kind of interesting. What do you conclude from that? kind of its ribbing.
Let's see. What? Oh, I see. It's a density plot of adjacent symmetrics.
Yep. What are those things? Well, let's look back at the original creature. So let's see, what do we have? EO25, I think we had. So let's look at. My God, what is this creature? Should we try a different embedding since it's just an ordinary graph? What is this thing? I mean, how do you make stuff like this out of something, so simple?
Well, that's the whole point, isn't it?
It is the whole point. I'm just always amazed at how simple these things can be and yet make such complicated stuff. Here, let me just record this creature before we forget it. Okay, what can we do to try and figure out what's going on here? All right, I think I can probably
Can we
do
do volumes for the large one?
Yes. Where did I have the volumes? Here we go. Also should probably look at the causal graph. By the way, do you have code that gets the in degrees as well as the out degrees for a ordered hypergraph?
No, I don't.
It's difficult, but I don't know why this is taking so incredibly long.
Well, it has to grow, it seems, from every point. So it's a quadratic time, probably.
I do not understand this thing at all.
Can you run the volume from a random sample of vertices instead of from all of them? Because the time scale for them might be about 6 billion.
All right. Look at this thing. I mean, it's just so frigging weird.
Why is it weird?
What's that?
Why do you say it's weird?
Well, just... Oh, God, the interrupts are not working.
Isn't it about what we want to get?
It is. It is. So it's a pretty simple rule here. I mean, it's, you know, let's look at that rule a little bit. That's basically just saying that every triple vertex here so is this, in fact, it's not a trivalent graph because there's tons of things. So the ones that are the active ones are the triples, right? Because that's a...
Well, triples and more.
Yes. And the ones that are two are just are now frozen, aren't they?
Well, temporarily at least. They, I mean.
Yeah. All right, so we see these little things, those little double edges, show up in various random places.
Well, the rule produces them directly, so of course they would show up.
Absolutely. But do they get broken open later? Yeah, they might very well get broken open later. Yeah, because I mean, even those, some of those two could go to the same one.
Right.
Oh, we're finally done here. Okay. All right, so let us try, I believe my hypergraph volumes thingy. Oh, for God's freaking sake. Okay, so that allows for vertices, random vertices. Okay, how many vertices did this puppy have?
Let me check.
Oh, look, here's the, like 20,000, right? How did you just type this rule in? I can send it.
30,000 in the final step.
30,000?
Yeah, I did type it. I mean, I have my own version of it.
Okay. All right. So instead of all, I want to go there. Random integer 30,000, comma, let's just say 100. That should be nice and fast.
Well, so it's, I mean, it's actually 29,347.
Okay. You know what? I need to. Why is that taking any significant time?
Well, it's going to try to do it for non-existing vertex, and who knows what happens then.
Are you sure it's not taking that time to just find out what the final state is?
Let me check. No, that only takes 0.7 seconds.
This is inside the graph code, which means there's an interruptibility problem inside the graph code.
inside the BFS.
Probably worth
Well,
reporting.
that's possible because it's very likely C++ code.
We probably should report that bug, that it's slow. I wonder whether the size of the maximum vertex degree is going to increase or decrease with time. I think I'm going to have to kill it. I think I have to quit here. Oh, shoot.
Increases with time.
What does?
A max vertex degree. And it's actually in a pretty interesting way.
Okay.
Up
What is
to
it?
step 20, it grows as about half of the step number. And after that, it grows as about double the step number. Although, well, I mean, I'm not sure there is actually a transition here. Let me send you the code to compute this.
That is interesting. Okay, if this is slow, then we're toast. You know what? I'm going to just limit that to size 10. What is the diameter of the graph? Do you know?
Well, it shouldn't be easy to, it shouldn't be hard to calculate.
happened there? Wait a minute. What on earth happened there? I don't understand this. Something goofed up here. I mean, this thing tries to make it into an undirected graph.
Well, it looks like a graph diameter is 24, assuming edges are undirected for the final state.
Okay, then why did my graph neighborhood volumes thing not work?
I mean, it doesn't even try to evaluate. Does it actually take 3 arguments?
Claims it does. Let's look at the code. After it. Oh, great. That's our causal graph.
Okay. Well, it's supposed to be 4-dimensional, so not surprising we can
graph?
see it. Well, isn't it? 3 dimensions plus time.
Yes. I mean, if we just happen to have found the universe. What the hell is that?
Well, how do you expect 4-dimensional graph would look like? I mean, since the ordinary one is 3-dimensional, I mean, it wouldn't be too surprising if the causal graph was 4-dimensional.
Yeah, I understand.
Okay, I'm going to try running it for 40 steps on my computer.
Well, this is computational irreducibility.
Well, it's just large. I mean,
what's that?
It's just large. It's not that we can't compute it. It's that it's large enough that it's hard to analyze.
It's disappointing if one this simple. I mean, this is the first one. Well, I don't know whether this is the simplest one that we can't analyze. Why is it doing a dynamic evaluation at all? This is a sick puppy, this thing.
So 40 steps has 250,000 edges at the last step. And it takes about 2.5 minutes to get it.
Okay. What can you say? What is its maximum vertex degree?
$76.
76. That was compared to 48, what we had before, right? How much memory is it taking?
Less, about half a gigabyte.
How many steps did you say you had it? 40 steps?
40 steps, yeah.
How much memory do you have on your computer?
This is 32.
How many steps do we think we can get it to? I mean, so let's extrapolate. Our growth rate is about 1.3. Can you see if you're maintaining that 1.3 ratio?
Let's see. I don't have states list yet. State list will probably take a while.
This thing is not even close to causal invariant.
Well, yeah, that's probably true.
So I'd be interested to know what it does for other initial
Yeah, it looks pretty stable around 1.3.
So what makes you think that this is hold on, let me just look at some of those other ones. Like, why do you think that one's more interesting than this one, for example? Or I mean, just because this one looks simpler.
Well, what makes it interesting to me is that it's three-dimensional.
You mean as opposed to being
One-dimensional. And I don't think we have seen a lot of three-dimensional ones yet.
Oh, why do you think is it three-dimensional? Is that what the measurements
Isn't
were
it?
showing? Yeah, the measurements were basically showing it's three-dimensional, I agree. But I haven't even seen a good two-dimensional one either.
Actually, can we figure how close it is to being three-dimensional?
Yes. Well, if we could get that hypergraph thing to work.
Well, we did have it for 25 steps.
Yeah,
So
okay,
what happened after that?
I don't know. But let's just do this.
Right.
$2.97.
Yeah, that's not too bad.
I don't think we're going to get better than that after 25 steps.
Well, who knows? Actually, can we do the same thing but with taking, well, take more. Anyway, instead of doing it for all of them, just feed, prefixes of it and see whether it converges to 2, 3, or what does it do?
Actually, it only gets down to 3 at the very, very last moment. I don't understand why this plot isn't straighter. This is a log-log plot. For power, it should be a straight line. Look, let's just take this thing. Okay, to be convincing here, let's do a list line plot of the cube root of this thing. Yeah, I would consider that. Well, it's not hopeless. It's not hopeless. If we do a list
Well,
line,
the thing is, if it's very close to the size of the graph, then it's obviously would
yeah,
work
if
as
it's
well.
very small, it's not going to work either. But I mean, you know, if we do it just to the linearly, yeah, who knows what's going on here? It's not obviously not three-dimensional, but it's still, I don't understand that ribbing. All right, so let's take this one as an example, but I want to go doing a little bit more hunting here. But take this one as an example. What the hell are we going to do with it? So we can grow it another, I mean, we can grow a piece of it. We could chop a piece off and then we could grow it locally. I mean, we could parallelize the growth insofar as it's, I mean, it is local.
Is it local?
Oh yeah, look at the
How do
rule.
we know that?
Well, it's local on the graph, on the hypergraph, right? You can see it.
I mean, obviously the rule is local.
Right. What's your point?
But I'm not sure the graph itself is local.
In what sense? You mean that there aren't long-range connections in it?
Yeah.
Yeah, okay, we don't know that. Long-range connections relative to what? Relative to some, and we could start taking some graph miners and things to try and see what's there. Can look at some neighborhood graphs. Let's do a little bit more hunting. This is a nice one. Oh gosh, what the heck is going on? I mean, we got to have some other updating rules, and we got to know what this thing does. I mean, we're not going to be able to trace it very far with, you know, in multi-way work and space. We should be able to do things like work out the spreading of a perturbation here, right? So if you flip one edge, how does that spread?
I would suggest you just do the cone in the causal graph instead. That's more reliable.
Yeah, I agree. Well, we can get that cone by just doing, I mean, okay, yeah, let's do this. That is an incredibly dense and non-useful causal graph.
Well, because it's supposed to be four-dimensional.
You know, if this thing is the universe, I mean, it's just embarrassing.
Why?
Because, I mean, somehow it's just a really simple rule. And well, I admit, I mean, that is what we kind of think might be going on, but still.
I mean, I guess the main question is whether it's class 3 or class 4.
Yeah, well, the question is whether it has some kind of analog of you know, what it would take to have particles and things like that in it. Okay,
Yeah,
so
and
that's
also
that's
how
our cone.
soon does it stop inflating?
Yes, if it does. What do we know?
Although it might have pieces of it stopping inflating, we are not
Yes, and we
noticing
don't
it.
have any idea. Right. But the fact that there's an exponent there, walk me through how that relates to, current inflationary models. That's
Well,
not the
it looks
same
like
thing.
it's inflating with, let's see.
Yeah, it's 1.3 to the
Well,
T.
it grows to 86 e-fold. Wait, no, 86. No, not e-folding. Wait, size. So let's see. Well, it's 0.5 e-foldings per step.
What? So by the way,
So you
that's
need about
basically
160 steps to get, at least, to get complete inflation.
You mean as in communication between all pieces? Look, that's basically the causal graph cone. I mean, that's the combined cone. So every little subpiece here is a cone.
Okay.
We should use aspect ratio to 1 for the layered graph plot. Let me make myself a note of that. What do we learn from this? Honestly, this doesn't look totally hopeless. I mean, if we were to look at this, this is in this updating order, this is the space-like hypersurfaces.
Yeah.
Won't it be a serious anticlimax if something like this turns out to be the rule? I mean, it's just such a bizarre and random and inelegant object. But
Well, how
unfortunately,
much simpler do you want it to be?
yeah, I mean, that's really about as simple as one can imagine. I agree. Huh. So, I mean, what we've done here, okay, let's just go on a little bit more of a hunt, and then I should go to sleep. You might say, how can you go to sleep when the universe might be out there? But I think, I don't know, somehow this is the feature of a seasoned hunting experience, is that I just want to look at one of these other ones and see whether it also does anything interesting. What was this one? This one was that one was the 2-1 whatever it is one, right? My God. Okay, that would be extremely embarrassing to lose the universe because we didn't record the rule number for it.
Well, I know the rule number.
Yeah, I know. Just. Okay, 1, 2, 2, 3, 3, 4, 4, 1, 4, 3.
Yeah.
Let's just try the next one of these just for fun. Just to see roughly what it does. Oh, that's interesting. Look at that. It just does the Magellanic Cloud, so to speak. That would be so weird if one predicts that there's sort of an orbiting universe that's separated from ours.
Well, it's not orbiting, just separate.
Yeah, I know.
Which?
But if they're pieces of our universe that just sort of spill off every so often and make separate pieces, that would be pretty weird. It has a certain flying machine character to it. Come on. This may have been a mistake. I don't know how big it gets.
Yeah, I mean.
Oh, look at that.
Well, yeah, it does.
Boy. So I wonder whether that's common to have things that get thrown off like that.
Okay, is it obvious that black holes don't do this?
No. It's not obvious at all. I mean, that's one way to have an event horizon, isn't it? I mean, one way to have no communication is it's just not connected.
No, but there is one-way communication, which means it has to be connected somehow.
Yeah.
But then there are
Well, and certainly the quantum information
black holes
stuff.
that do weird stuff.
What's that?
But then there are always rotating black holes that do.
Well, yeah, right.
weird
They just have,
stuff
I mean,
like that.
but nobody's so far observed a naked singularity. It's always, it seems like, you know, J is less than or equal to M. But there are a bunch of critical ones that are seen. But I mean, the quantum information, you know, the sort of the laws of physics are reversible doesn't really work if if a piece of the universe breaks off.
Yeah.
All right, which one was that? That was 1, 2, 2, 3. Let's just try this guy here. Is it obvious to you that let's see. This left-hand side is a useful one. You know what I'm saying? I mean, so that, okay. Because I mean, we're doing a specific search here for a left-hand side.
Yeah, I mean, I think it makes it more likely to find. Well, I mean, the point is we know this left-hand side is somewhat interesting.
Yeah.
So
Yeah, I agree. As opposed to a self loop or something, which is going to be complete. Oh, look at that. That guy threw stuff off as well. What the heck makes it throw something off? All right, I do not understand how it throws things off. Okay, can you explain to me how that throws things off?
well, the center vertex was connected to something else.
What?
So if the center vertex on the left was connected to something else, it would lose it.
Yes, that's true. Okay, but why does our friendly rule that we were just looking at not throw things off then? Because,
Well, I mean, it's more densely connected for one thing. I mean, on the same argument, it could.
yeah.
But maybe because it's more densely connected, it's much less likely.
Let's see what that one looks like. Wait a minute, that's extremely similar. That's 3 outgoing. What's the difference between these? 1, 2, 2, 3, 3, 1, 3, 4. Oh, I see. There's a difference. No? What's the difference?
Can you show both of them side by side? Well, orientation is different.
Yeah.
Oh, wait, does it actually make any difference? I don't think so. No, then it's just evolution order that's different.
Yes.
Huh.
That is interesting. So that shows one, that guy versus that guy. You know, they're plausibly similar, actually. All right, so let's look. I am curious about whether we can prove that some of these things can't throw anything off.
Well, I don't know, but it might be difficult.
Why aren't you interested in that rule there? I think you should be.
Yeah, it looks pretty similar actually.
All right, I'm going to clear this. I'm going to. I think we need to look at some of these others.
Okay, I think I have a random evolution order working in a branch.
Okay, can you try it on this rule?
I mean, it doesn't do normal one anymore, but
Can you try it for this rule?
yes, that's what I'm doing. I mean, I hope it's actually working correctly. I'm not completely sure. Right. Somehow it doesn't grow nearly as much anymore. The random one is weird. I'm assuming it's actually working properly. It grows much slower.
There's some interesting ones here as well. This is very fertile, this area.
Do you want to try running the random one?
Yes, but hold on 1 second. Not if it's going to mess up my whole
Yes, it
screen.
will.
Okay, so let me just hold on 1 second. Let's see your screen.
Okay.
Actually, just 1 second. I just need one thing to eat. I'll be right back. All right, what is all that stuff? Is that different random runs?
Yeah.
What's the plot?
That's ratios. But the fact that they go up at the end, I don't think it has anything to do with 40 steps. It's because it tries to finish all the generations or something like this. Because it moves if I increase the number.
Let's see this. Let's see the graphs. Well, it's not qualitatively different. It's not like the whole thing fell apart from random updates.
But it grows much slower.
So, why is that surprising? I mean, it's not bin packing the growth in every generation because you're showing it by generation, right? If you unpacked it by events, right? We showed the amount, we showed, growth by your clock here is slower, right? Because you're not packing your generation here. It's like throwing a bunch of marbles in something and you don't, you do the couple of packing, there's a lot more of them.
Right. Yeah, it makes sense. Yeah, so what I want to know if it slows down growing. I mean, if it actually slows down, or is it because some generations are incomplete?
I bet it becomes more difficult. Let's see. It depends how good your greedy bin packer is. Because in this thing, there's probably fewer and fewer places. Actually, it depends on what it means by random updating. I mean, so looking at all the events.
Well, this is what I mean. I pick the random match at every step from the entire set of matches.
Okay.
So it's actually, I mean, it's uniform. I mean, to the extent that rand from C++ is uniform.
Mm-hmm. What is that thing down at the bottom there?
Well, it's pretty much the same thing, but for 60 steps. The ratios. Okay, that's probably too many.
Let's go back to my machine for a bit and let's just look at.
Okay.
This is a remarkably fertile domain here. We're just seeing a lot more. Just take a look. There's just 3 on the left-hand side. I just want to see whether. Let's just go 2 to 3. There are only 15,000 rules. Of this type, we can just enumerate all of them. Well, that's a peanut form. Is it really true that none of these rules are connected? Can you just help me with this for a second?
Let's see.
Well, let's just do random sample.
The right-hand side should be in list.
It's much crazier than that. There we go. More like it. Okay, that's the number of connected by connected rules of that type. Okay, there are no prize specimens in that collection. Nice that parallel map monitored gives me an ETA. I know I've got like 3 minutes to wait.
Yeah. Well, the reason I did parallel map monitors is that I was doing this, stuff for my PhD, which took a long time. Basically, a bunch of differential equations for different parameters.
Uh-huh.
And I was running them about like few hours at a time. So ETA was useful.
Sure. Yeah, this is cool. All right, 3 minutes. This is very frustrating to wait for this thing. All right, I'm doing the 3-2 goes to 4-2, as you can see. Which we can do exhaustively with 4 symbols. I don't know how the symbol count, affects things. I mean, there's clearly unbelievable numbers of symmetries here.
Yeah.
I don't know whether the enumerate Wolfram model rule, is that an add thing? I can't even remember whether whose code that is now. If this finds anything. All right, so what is our strategy for these ones that are kind of complicated and where we can't tell what's going on?
Well, I'm now trying to figure out what happens in the random case.
Yes.
So apparently it's still three-dimensional, looking at the ball volumes, or at least close to it.
Well, so you're claiming that if I start, what about in the causal graph? Can you measure the dimension of the cones? By the way, is the result that you've just given, is that true following directions on the graph or assuming it's two-way?
Let's see. Well, what do hypergraph neighborhood volumes do?
It's two-way. That assumes two-way.
Okay. Well, I want to understand what happens to the ratios, because looks like it slows down growing, but I'm not completely sure. So you really need this, complete generations stuff.
Why is that going to help?
Because I want to know which of the generations are complete and truncate in that.
You mean in the random updating?
Yeah. I mean, of course, random updating is not implemented by far, so.
No, but I mean, you're saying
I
the
can
random
run it
updating, you
here.
just have no idea where the generation, how are you slicing it by generations right now for the random updating?
Well, I can compute generations later on, because I know what depends on what.
What did this just do? That was just weird. It slowed down right at the end.
Well, because not all kernels were used anymore.
Look at these. Those are very complicated slow growth. Look at that creature. My God. All right, there are 5. I would say that drum roll was definitely not exciting as it might be. Well, there are 5, and a bunch of them are identical. So there are actually only 2 separate creatures here.
Yeah.
Let's just record those creatures. You know, ever since I started, I type print cells, and every time I type print cells, I end up typing prints instead, and I have no idea, because I can't imagine that the total number of times in my life that I've typed that word is very large.
Yeah.
Okay, let's look at the slow growers. Okay, so this basically shows us that in this structure of rule with non-random whatever. Okay, so this is 3242S4.
How many are there in 3 to 5?
Of this type,
Yeah,
where it's
3
just
to the 5 too.
no. There are lots with that, but this is with the particular initial condition of just a prong, right? This is just with this left-hand side.
Yes, I understand, but I'm saying with this left-hand side, 3 2 to 5 2, how many are there? Because that's a
4/10th.
three-dimensional one, you know, in it.
1,000,000. I mean, it's easy to do that overnight.
Yeah, might be useful.
Yeah. No, I agree. That one is perhaps worth doing. I mean, we can get some sense. Okay, so that's, I would like to do 2 to 4. Oh, actually, these ones are with 4 symbols, right? Whereas that one, how many symbols are in that one? And by the way, notice that all these rules have a 0 node on the left that is not appearing on the right.
Yes, so it has 4 symbols, not including 0.
Okay, so that's 1 of a million, 1 in a million. So this case, so do you think there ever going to be is ever going to be an interesting one with oh my gosh, there's a maybe interesting in that category. Wow, look at that guy. Look at that guy. Wowee. Look at him. Look at it. It's a beaut. It's look at how simple that rule is going to be. Oops. Look at that rule. Let me record it immediately. What the hell is so? If that thing isn't knitting, I don't know what it is doing. Look, it's going to knit. It's going to make a. I think it's going to make a coat. You know, it's going to make a 2-dimensional thing. I think. Let's try running it a bit longer. My God, look at that thing. My gosh. Why is this taking so long? Events count. By the way, is it trivial? Would it be trivial in this? Oh, look at that. Okay, you have to admit, that's pretty remarkable. Look at that thing.
Yeah,
Look at that tiny
it
rule.
is interesting.
So this means that in the 2 goes to, so that's in 2 goes to 4. So I didn't think we'd find anything there. I assume we won't find anything in 1 goes to anything. That's obviously trivial, right?
Well, it would be nesting.
Yeah. Yeah, lots of pure exponentials. Two goes to 4. Let's try 6 symbols, although I can't imagine it's going to make any difference. Do 1,000 of them. Those are different. God, this is such a weird business. Look at that thing. Oh, that's amusing. They're identical. No, wait a second. What is happening here? Is that the same thing with just a different ordering? I think it's the same thing with a different ordering.
Well, it reverses. Well, yeah.
Yeah, literally, it's just one of the edges is reversed. So my guess is that's what there is in that space, in that particular space. We'll try one more time, just for good luck. I think we're just going to find lots and lots of copies of that guy.
By the way, if you want to look at random evaluation order, I could send you the evolution object. That's perfectly compatible.
Okay. Hold on. 176. 110, 176. Boring. All right, my guess that's pretty much what there is in the just yeah, those are basically equivalent. What a terrible slug. Why is that one even vaguely interesting? It looks completely and utterly boring.
Wait, what does it skip sometimes?
I don't know, let's find out. Boring. Very surprised the linear occurrence system didn't pick that up. This is not such a common thing to see happen as that there's repeat. I mean, we can find this with fine transient repeat. All right, and assume it was at 3.5, we're just replete with interesting stuff. I need to go to sleep, despite the Excitement of the hunt. I need to be ready to hunt another day. Wow, 9 may be interesting, so I bet they're all worms. Oh no, actually we're off in the interesting zone again. So I wonder if these are the same as what we've seen before. I bet they are. It's a fairly good sample, actually, of just interesting exotic things.
Yeah. I mean, they don't. I'm not sure. They don't look that similar.
To what? To things we've seen before? Well, here.
I mean,
arguably.
there is some of them definitely similar.
That one is symmetric, which is fun. I haven't seen that too often. Let's just see that one there, that second to last one. That is interesting. We really haven't seen that many symmetric ones.
Yeah. What does the rule look like?
Great. What the heck is that weird thing? What do you think that is?
Well, we know what it is. It's middle goes to.
It's what?
I mean, it's 0, 1, 0, 2, 0, 3. It's just weird layout.
Yeah, because the right-hand side is collinear.
Yeah.
Yeah. Look, it's pretty obvious we can enumerate all of these the ones of this size, we should be able to enumerate all of them. Because we just got to look at canonical hypergraphs on the left. What can I do with a WXF file? Read it in.
Just import it and, it will give you the expression.
That's pretty cool, actually. Okay. This is in the wrong file. What's this?
Wait a second, did I send you incomplete? Can you check the other one again?
I think when I dragged it, it says taken out in notebook, so.
Can you say store now? Just click on it, what will happen?
Nothing.
That is weird.
Well, because it doesn't have it anymore.
Well, then how come it's 8 megabytes? I mean, 7
because it remembered
megabytes.
that it should not say store now when it no longer has the data. So I think you have to press the store now.
Well, usually it doesn't. Interesting. How do I export them then? No, that's really weird because I exported just, I mean, I did export of the expression.
That's weird.
Full form of which does contain everything.
All right, I can't explain that. I need to go to sleep. But if you're able to get something which is actually an option that allows random evolution, that would be super useful.
Yeah, I know, but that's more considerably more difficult than just doing
Why?
what I did.
Why?
Well, because it should also work for symbolic code as well. And it should probably be consistent with symbolic code.
We don't need the same random numbers. I mean, it would be amusing to have the same random numbers, but I guess you'd have a random seeding option.
Yeah, but if there is a random seeding option, it should produce the same things.
I know, but if without a random seeding option, nobody's going to know.
But we should have a random seeding option.
It should, yes, it should. It
should,
but
it should be reproducible.
I know, but it will be interesting to see what this looks like without that. I mean, basically, can you look at a causal graph? Can you look at a causal graph from the random evolution? And this was the aspect ratio 1 causal graph for the layered graph plot. Let's look at what that looks like.
It's plotting it.
Yeah, let me see your screen. What's that picture there?
Which picture?
The one below. This log line plot. Oh.
This is volumes.
That is a remarkably straight line. What is the slope? Is it 3?
Well, I mean, it looks close to 3. I didn't actually measure it. Maybe 10,000 events is too many.
I think the word headdress has a double D in it. I'm just sending mail saying, let's discuss making monitor to headdress. Like one of these modifiers we could put on arbitrary functions. Anyway. That's 10,000 events.
Yeah.
Well, can you kill it? Can we try doing it just for...
Wait, what is that? Okay, it's killed it too well, apparently.
You loaded the Wolfram model packlet. Yeah. Okay. See, one question is what the mean field theory, what the analog of mean field theory is for these creatures. You know, can we estimate things based on some, you know, if we look at little subgraphs there, maybe there's some statistical properties of the subgraphs that we could use to build a mean field theory. What the hell is that? So the hair at the bottom might be because of the random updating stuff, I guess.
Well, it just went further in one place than in others.
Yeah. Why is there so much density on the right?
Well, I don't know. Let's do another one.
How big could we grow these things? I mean, assuming, okay, so that's what does mean field theory look like for these?
Well, I think we first need to figure out what manifold are they, if any.
Yes.
Then, you know, we can estimate coordinates on it, which
Right.
would definitely help.
All right, I have got to go to sleep. All right, well, this is fun. We're making progress. Really
Yeah.
making progress. I mean, look, it is very encouraging that there's stuff as complicated as this so easy to find.
Yeah.
I mean, we know this project isn't going to be easy, so we expect it's not going to be easy. So, but I mean, I'm a little concerned about if in the case like this, what are we going to do? Because just keeping on running it is not obviously going to help. It may just go on produce. I mean,
well, I mean, right now it looks like the bottleneck is not how far we can run them. It's if they grow large enough, we can't even analyze them.
Yeah. Right. I mean, the manifold limits are that's an obvious way to characterize, to sort of tell a story around the limits. Okay, I've got one thought for you, and then you got to go to sleep. So, imagine you're doing computation with Turing machines. Then there's certain constructs and arrays and so on. There's certain constructs you invent, like fold list or something like that, right?
Yeah.
But now imagine that you're doing computation with hypergraph rewriting, and then you ask, well, what constructs would you invent? But then you say, well, gosh, the kind of constructs we might invent are things like manifolds and particles and so on. The constructs of current physics. But my question is this: if you start from the beginning again, and you're describing things in terms of hypergraphs and so on, what are the sort of aggregated physical things that you start to describe? That is, describing space and particles and so on is, that's one essentially programming language for describing what's going on in these systems. The question is sort of, might there be an alternative ones? Anyway, that's just my thought. I mean, it's like, for example, this arbitrary dimensional space is an example of something which is a construct, right? I mean, like the whole idea in general relativity of curved space, space-time, and then the idea of curved space. Those are kind of ideas about ways to describe the physical world. So, for example, the idea of a varying dimensional space is not really an idea that's on the radar for, you know what I'm saying? And so, if you, I mean, it becomes on the radar when you look at systems like these, but it's not when you're thinking about continuum, spaces. And so I'm just
not obvious. I mean, there are compactified dimensions, which is
but that's a really lame version. It's a really lame version.
Yeah.
But I mean, so that suggests kind of, in a sense, a data structure for describing the physical world that we have not seen in physics. Just like I could imagine, don't know it yet, that particles represent localized stuff, and space-time sort of deformations of the curvature and so on represent very global stuff. And maybe there's something different and intermediate between those two that you could imagine. I mean, I don't know, like for example, in these graphs, the fact that we can have a lot of returns to the same node is kind of a weird thing. It's kind of like a in terms of space, that's like, it's sort of like a cusp in the manifold or something like this. Not quite that, but anyway, I need to go to sleep. All right, to be continued.
Okay.
All right, see you later.
See you.
Bye.